All right, today we're going to go through position and time graphs. So this is just reading graphs the same way you've done plenty of times before, but instead we're looking at position versus time. So while you've looked at different graphs, mostly in math class, and tried to figure out different patterns, we're going to do the same here, but just talk about how far we've gone, how long it's taken, and then we're going to talk about how we get equations from these graphs. So graphing, I like to say, is kind of like the art of science. Like scientists are not very artistic, but we take the data that we collect and we can turn them into visual aids and graphs. So graphing is super important. And the easiest graph that we are going to start off with is position time. For all position time graphs, time is an independent variable. It's what we are controlling. We could stop at any point in time. We could start at any point in time. So it goes along the horizontal axis, and your position depends on the time that we stop at. So your position is dependent, and that means it goes along the vertical axis. For position time graphs, there's only two skills that we need to know, and it's reading values off the graph and then finding the slope of the graph. So on this graph, we're going to look at someone walking to school from home, and we're going to go through answering a few questions about it. So where are they starting from? Well, if we look at the farthest left data point on our graph, we are starting at 0, 0, meaning we're probably starting at home. We have a distance of 0 meters, displacement of 0 meters. Where is the student walking to? They're going to school, and the end of our graph is reading at 80 meters south. So our information on our y-axis is actually telling us that. So how far is the student's home from school? The distance is 80 meters to the south. How long does it take for them to walk to school? Well, if we're only going to 80 meters, our time on the graph stops at 60 seconds, which is a pretty dang nice walk. And after 30 seconds, how far has the student walked? Well, we're coming over and looking at our 30-second timeline here. So we're looking at our 30-second timeline and then just going straight up to read what the position is, and that is 40 meters south. And how long did it take the student to walk 20 meters? So we go to our position at 20 meters and go over till we intersect the line and read the time value, and it's 15 seconds. So all of that information can be read from the graph. And if we are reading from a position time graph, we're really giving ourselves information about the position. And we need to find the slope of the graph to really get more details. So if you remember, our slope equation is m is slope, and it's just your rise, or how much you go up the y, over how far you run along the x. So in this case, we are going up to 80 meters and then over 60 seconds. So our slope is about 1.3 meters per second to the south. Now, we're looking at meters per second. So what information does that give us? Well, position versus time is the same thing as d over t. So we're getting a velocity based off of that. Now, the other thing to remember is the expanded version of our slope, which is change in position over our change in time, or if we put it onto our x and y coordinates, this would be y2 minus y1 over x2 minus x1. This reads the exact same way as that original slope equation. So then if we take it using our variables and we simplify it, we can see that it's the same thing as our velocity. So whichever one you prefer to use, if this makes more sense to you, or if y2 minus y1 over x2 minus x1 is just ingrained in your subconscious, then go for it. So by comparing graphs on the same scale, we can learn more about what the shape of the graph tells us. So if 3 siblings walk to the same school 300 meters east from the same exact house, we want to decide which sibling is the fastest and the slowest, which is kind of rude. I feel like they should all walk together, but that's okay. And then we're going to calculate the slope to determine their average velocities. So for Alfie, we're just looking at the rise over the run. So they're going their 300 meters east to the school, and it's going to take them 240 seconds. So when I plug that in my calculator, I get 1.25 meters per second east is my average velocity. So just by looking at the total rise over run, I can give myself an average velocity. Then Beth's got a little pep to her step. So she's going 300 meters, but it's only going to take her 120 seconds. Notice how this graph still goes to 240 because that's what Alfie needed, but we can see it ending at 120. If we would have 120 listed all the way over here on our x-axis, then it would look skewed because the graphs would look the exact same, even though they are showing very different information. So we plug in our 300 meters in our 120 seconds, and our average velocity for Beth is 2.5 meters per second. So she's picked up the pace. Then we've got Cameron. So Cameron is going the same 300 meters, but it is taking them 180 seconds. So that averages out to 1.6 meters per second east. And again, if we had put 180 all the way at the end and kind of cut our graph off there, and not extended it all the way to the longest time frame out of the ones we're comparing to, it wouldn't look the exact same, and we would have to really do some calculating. So a steeper slope means that they're moving faster. If we go back and look, Alfie took the longest, and he's got the most steady incline. Beth was ramping it up, literally, and Cameron was right in the middle. So the steeper the slope, a faster velocity. You can also think of it as if it was something rolling down the slope. So if you rolled a car down this pretend ramp, it would go pretty fast, but it would go much faster on this graph. Lots of different ways to think about it. You can also have multiple lines with different slopes. So this person is not walking at a regular pace the entire time. Well, let's look how we can break it down. So they're keeping a pretty steady pace because it's a straight line between these 2 points. And then they stop. Let's say that they're waiting for a car to pass or answering a text message or checking to see if they brought lunch. And then they speed up, so maybe they're crossing the street after waiting for that car to pass, and then they go back at a steady pace again. And I can tell that they sped up because the slope here is steeper, so I know that their velocity went a little bit faster. So we're looking at what time interval the student is moving the fastest. And that is all dependent on slope. So we need to maybe look at two of our steeper looking slopes, which would be this section right here and this one right here. So this one, we're going 40 meters in 22 and a half seconds. That's a weird breakdown of time. 15 divided by 4 is not smooth. Anyway, or we're going 10 meters in approximately 2.5 seconds. So if we calculate that out, or we can just look at it pretty intensely, 33.75. Sorry, I don't have a calculator. I kind of made those numbers up off the top of my head. So 33.75 seconds and 37.5 seconds is the interval when they're going the fastest. Now, if we're going to determine the average velocity in that time interval, we're going to take a look at our change in distance over our change in time, which is the same thing as our rise over run. So we go from our D2 is 50, our D1 is 40. And then they gave us our time interval, which starts at 33.75 and moved over to 37.5. So when we calculate it and simplify it down, we get 2.6 meters per second west, because our velocity is a vector, so we need to make sure we include the direction that they are heading. So what is the meaning of the horizontal line right here? Well, we already decided that that's when someone is stopped. Now we're going to prove it by determining the slope in that section. So if I'm looking at rise over run, I'm going up 0 and dividing it by a time. I don't even care what that time is, because 0 divided by anything is still going to be just 0. So we literally can prove that we did not move at all during that time span. So how is this student's average velocity for the entire walk to compare with the first student's average velocity? So while this is a bigger graph, so I'm going to stay here for a second. Our first student walked 80 meters in 60 seconds. So did this graph. It's just they changed their speed at some point. So they have the same distance, magnitudes are the same, and even though we changed velocity and their directions are a little different based on where they're walking from, they both traveled the same average velocity, because when we're talking about the average, we're just looking at the very start from the very end, and whatever happens in the middle happens. So let's look at this position time graph according to what someone did during track practice. Track practice apparently only lasted 40 seconds long, but if we're going to describe the motion of the runner, how would we do it? So the runner is running for 25 meters, then they stop for 5 seconds, runs for another 25 meters, stops for another 5 seconds, runs for 25 meters, stops for 2.5 seconds, and then they run all the way back to the 0 start position. So over here, you can see they said they changed direction and runs back to the start. And I can tell that because my position was going farther away, and then it comes back to 0. And my position is based off of where I began at. So they either turned around or they were on a track and started kind of heading back towards where they were coming from. Either way, they got closer instead of farther away from their starting point. Now, this is a really weird interval for someone to be completing, but whatever works. So what are we doing in the sections with horizontal lines? Just taking a 5-second break, because our horizontal sections are 0 slope, meaning our velocity is 0. Find the average velocity of the runner in the last section. So our velocity is our change in position over our change in time. So I'd actually start down here would be my D2, because that's where I ended. So 0 minus 75 meters north. And then my time would be my 40 minus 27.5 seconds. And when I calculate that out, I'm going to get a negative meters per second. And all that we're saying with that negative sign is that our direction is not going away from us, but it's coming back. So instead of them actually still running north, which is what our position graph says, we're actually at that point flipping it to saying, okay, so it's a positive 6 meters per second south. So that negative sign just flips our direction. What's the runner's final position and overall displacement? So your final position is right here at the very end of your graph. So it is at 0, which means that we started and ended at 0. So our displacement, or where we started and where we ended, is 0. So this is like if the Flash ran halfway across the world and then ran back. We wouldn't know that they went anywhere because they're so fast. So key ideas to remember. Your position time graph shows the position of an object as a function of time. And we have to remember our reference point. So the horizontal axis of a distance time graph or position time graph is going to refer to our reference point. And the slope of a graph gives us velocity. So the equations that we want to remember from here is that slope is our average velocity, which is either d2 minus d1 over t2 minus t1, or a change in distance over a change in time. You can also use the m if you are more comfortable, remembering that slope is y2 minus y1 over x2 minus x1. You just need to remember that slope is your average velocity. So describe, using diagrams, how the slope of a position time graph relates to the object's average velocity. Include horizontal lines and lines with negative slope. So a horizontal line means that the object is stopped. The slope is 0, which means our velocity is 0, and the position is not changing no matter how much time is passing. A positive slope means that we're moving with a constant velocity in the positive direction. And the larger the slope, the steeper the line, the faster the object is moving. The steeper the hill for a car to roll down, the faster it will go. And this graph right here is showing that our reference point is where we're starting here at 0, 0. Now, a line with a negative slope means that we're moving with a constant velocity in a negative direction. And when we're moving in a negative direction, all that we're doing is taking whatever direction is labeled on our y-axis, and we are going in the opposite. So if we're saying north, then our final is actually going to be south. If the axis is labeled west, then our final velocity is moving east. And again, the steeper the slope, the faster the object is moving. And this graph is showing us something that starts other than the reference point. So our reference point might be the movie theater, and maybe we started at the bakery, which was this far away. I have no numbers, but that's the idea.